Hi everyone, this is Ray from the University of Utah. Today I'm going to present our brief announcement about how to design the distributed algorithms for the CNNs. Our paper is focusing on the convoluted layer in the CNN network. It can be expressed as the following expression, and our goal is to design the communication-efficient distributed algorithm for the convoluted under given P processors, and each processor has M words local memory. In this presentation, to make it easier to explain, we will use the MATMO as an example to demonstrate the main flow of the paper. The overall approach of this paper can be summarized as the following three steps. At the beginning, we will construct a two-level tiling view under the global memory assumption. We will use MATMO as an example to present the structure of the two-level tiling view. In the figure, the blue box represents the problem space of the MATMO. It will be partitioned into different green boxes, and each green box represents the workspace of a single processor. The workspace of the single processor will be further tiled into different local tiles. The volume of all data footprints of a single local tile can fit in the local memory, and each processor will run a tiled loop nest surrounding the local tiles to complete the whole workspace. Once we have the two-level tiling view, the next step is we construct a tile size optimization problem, and the goal of the optimization will be reduce the total communication volume. Once we obtain a global memory solution from the optimization problem, we'll move to the last step, that is, design the distributed memory algorithm from the global memory solution. We will then introduce how do we construct the tile size optimization problem. Under the two-level tiling view, each processor is running a tiled loop nest, and the body of the loop nest is the computation of a single local tile. Every time the processor moves to the next loop iteration, it will request the necessary communications from the global memory. Therefore, for a fixed loop order, we can derive the communication volume from the global memory to the single processor. On the left, we are using the loop schedule IJK as an example to present the tile size optimization problem we construct. The objective function will be the total communication volume. The first constraint implies there are in total P processors, and the second constraint is the local memory constraint. We can solve this problem by utilizing the Lagrange multiplier and the KKT conditions. And we will show a solution structure overview in the next slides. The structure of the global memory solution can be expressed by the following figure. If we do not have enough local memory such that P multiplied local memory size is less or equal to the tensor C size, the solution we derived will not spread processors along K dimension. This is shown as the leftmost figure, and it is equivalent to the 2D MATMO algorithm. On the other hand, if the local memory is enough such that P multiplied local memory size is larger than the C size. The solution we derived will spread the processors along all the dimensions, and the C footprint of the workspace for a single processor will not be tiled. This schema is shown as the right part of the figure, and it is equivalent to the 2.5D plus 3D MATMOL algorithm. Inside this branch, if the local memory is larger than some point, the solution we derived will always stay on the 3D algorithm. Otherwise, it will stay with the 2.5D algorithm. In this slide, we will demonstrate how we build the distributed memory algorithm utilizing the global memory solution we obtained before. In the global memory algorithm, each processor is running a local tilde loop. The tilde footprint of the first iteration is shown in the figure. When we move to the next iteration, it will keep reusing the C tilde and load the new A tilde and B tilde from the global memory. We can observe that the processor along the K dimension is using the same footprint of C, and the same property applies for A over J dimension and B over I dimension. Based on this property, we create the distributed algorithm as follows. We will replicate the footprint of C along all processors of K dimension, and we distributed A footprint along J dimension and distributed B footprint along I dimension. In this example, our processors at the left side holds first half of B footprint, and our processors at the right hold second half of B. So when the tilde loop nest runs in the first half iterations, all processors on the left will broadcast data to the right. When the tilde loop nest runs on the second half iterations, the broadcasting will happen from right to the left. We can use the same method to build distributed algorithm for CNN, and we will briefly go over the necessary key points for extension. The optimization problem of CNN would be too complex to find the analytical solution. Therefore, we work on to create a simplified problem which is solvable. We will use this simplified problem to create a lower bound and the upper bound for the optimal solution of the original problem. If we set the memory parameter to be same as the original, we can get a lower bound cost. However, this lower bound is not reachable because of violation of original memory constraint. We will then reduce the memory parameter for the simplified problem such that the simplified solution we found is not violating the original memory constraint. This makes us find a valid solution of the original problem, which is an upper bound of the original solution. If the amount of reducing the memory parameter is significantly smaller than m, the upper bound solution we get will be extremely close to the lower bound. At the end, we will present a summary of the CNN solution. It can be summarized as a decision tree. If any of tensor size is larger than local memory minus delta multiply p, the distributed algorithm we construct will be analogous to the 2D MATMOL algorithm. Otherwise, the algorithm we construct will be analogous to the 2.5D or 3D algorithm. If the local memory is sufficiently large, it will shift to the 3D algorithm. Otherwise, it will stay with the 2.5D algorithm.